In this video, we're going to have a look at what we understand by the term dynamic equilibria. So at GCSE, you've probably come across these reversible arrows here. So this at GCSE, you'll have talked about how A and B can be converted into C and D, but C and D can also be converted back into A and B. Now, equilibrium is a little bit more complicated than just a reversible reaction. We need to think about what we mean by actual equilibrium. So dynamic equilibrium's got kind of two contradictory terms. We've got dynamic, which means moving, and equilibrium, which means in some way equal or still. So what do we mean by dynamic equilibrium? Well, the first thing we need to understand is you can only have a dynamic equilibrium in a closed system, because you can actually only go backwards if your system is closed. For example, if I was to react A and B, and they were to make C and D, but D was a gas, and D escaped from my beaker, then D could never actually react back with C to turn back into A and B. So it has to be a closed system, so that there is a chance for C and D to recombine to make A and B. And when we're in equilibrium, we've got this natural balance, a balance between the reactants and the products, and that balance is going to remain once we're in equilibrium. So think about it like being on an escalator. If you're on the down escalator but you're walking up it, if you achieve a natural balance, a place where you appear not to move, it's because you are moving at the same speed. So you and the escalator are going at the same rate, and yet nobody looks like they're moving because from the outside you seem to stay still. And that's exactly the same as what's happening in equilibria. A and B are turning into C and D, and C and D are turning back into A and B, but they're doing so at the same rate, and therefore it appears that nothing is changing. Things look like they're staying the same. They are staying the same, the amounts are staying the same, but they are continually changing into one another. So this is what we understand by dynamic equilibria. So we're going to write down our first key feature of a system that is in dynamic equilibrium. To have achieved dynamic equilibria, this is our first key feature. So there we have it. The rate of the forward reaction is equal to the rate of the reverse reaction. If we're in dynamic equilibria, then that will definitely be true. So what I want you to do is take out a ruler and see if you can look at this graph and find the time at which equilibria has been achieved. So equilibria is achieved when the rate of the forward and the reverse reactions are the same. So I've put my ruler at the point where the forwards and the backwards reactions have the same rate. And I'm going to draw a line down to the x-axis. So if I just get rid of the ruler now, and then we can label on our forward and reverse reaction. Now we know that the forward reaction will start off quickly, and the reverse reaction would start off slowly, because at the reverse reaction at the beginning there are no products to go backwards, so we know that those two are true. And then we can look at where the rates, because this is a graph of rates, where the rates are equal to one another, so where the two curves meet, and that is happening at 30 seconds. So that's our first feature of dynamic equilibrium, the rate of the forward equals the rate of the reverse. And then our second feature is about, once we're at that dynamic equilibrium, how things appear to remain constant, how our macroscopic quantities, our amounts, aren't going to change. So let's just write down our second feature of dynamic equilibria. So our second feature is that the concentration of the reactants and the products are going to remain constant. So if we were to say at the beginning we had a lot of reactants and no products, we can see how they change over the course of the reaction, and we can find the position of equilibrium again. So pause the video and see if you can work out where equilibrium is achieved by considering that second key feature. So there we go. If we have a look at that second key feature, we can see that at 60 seconds those two lines level off and remain constant from that point on, and therefore we have achieved equilibrium at 60 seconds. Now in this equilibrium, and it's an equilibrium that lies to the left, what we mean by that is that at equilibrium there is a higher concentration of the reactants than of the products. So we've got more reactants than we have products at equilibrium, and that would be an equilibrium that lies to the left, lies close to the reactant side. So even though both are present, they're not in equal amounts, there are more reactants than there are products. So how would that work for lies to the right? So have a go yourself, see if you can work out one, where equilibrium is achieved, and two, what there is a higher concentration of. So there we go, what we can see is that the reactants fall again during the reaction and the products increase. And at equilibrium there is more products present, the line for the products is higher than the line for the reactants, and we can see that those two lines level off, remain constant from 80 seconds. So equilibrium is achieved at 80 seconds. So it's important that you can interpret these graphs, but the main thing is that you know these two key features. The rates are equal at equilibrium and the concentrations remain constant at equilibrium.